Okay, so this is the title of my talk, Black Hole Entropy from Indistinguishable Quantum Geometry Excitations. So before, at first I want to thank Professor Majhi for giving me the opportunity, because the registration was closed and then anyway. Okay, so before just starting this talk, I want to just summarize on the board that what is the precise thing which I am going to talk about.
Sir, ठीक है
Yeah.
हाँ ऑस्ट्रेलिया में
ठीक है. Hello.
Yeah.
So,
Yeah.
okay. So, what do we actually mean by this indistinguishable quantum geometry excitations? So, we have actually heard two of the talks about the issues which I am going to talk about, one by Professor Partha Mitra and one by Professor Partha Majumdar. So, I will just draw some few pictures so as to focus about the central issues of what my talk is going to be about. So, suppose this is the black hole event horizon, and this is a section of the space-time which I am talking about, and these are the Cauchy hypersurfaces. So, any of this section of the black hole horizon is a spherical, so topological sphere. So in this quantum geometric language, this is actually built up of these punctures, which Professor Mitra talked about, which carry these spin-up representations. Sorry, not spin-up, SU to spin representations. The quantum number J, which carry this kind of spins. So, what people generally do in case of this LQG, so this is the LQG description of black holes. So, what people generally do is the calculation of the entropy, where these punctures are considered to be distinguishable. So, what I am going to do here is that what is the scenario and how is the entropy calculated if the punctures are considered to be indistinguishable. So, this is precisely what my talk is going to be. Now, I will start this slide. Okay. So here is the outline about the talk which I am going to present. So at first I will introduce the isolated horizon framework very briefly. Then where these punctures come from. So I will talk about a few words about the quantum geometry, that is in loop quantum gravity, how the spatial geometry is described. And then I will briefly introduce very pictorially the basic structures of this quantum isolated horizon. Then I will review the microstate count, so the Majumdar formula, and from there how can we compute the entropy, the Bekenstein-Hawking area law, in case of distinguishable punctures. But although that is a review, that will give me a very crucial lead to how to calculate the same entropy for indistinguishable punctures. So that's why I will do this review. And the link is that from the very fundamental formula for the microstate count, which is related to the SU2 Chern-Simons quantization, we can just by through some very basic algebraic steps, we can go to the very familiar formula of ideal gas statistics. So that I will show, and from there it will be very trivial to to go to these indistinguishable puncture cases, where finally the entropy will be calculated. And I will end with some concluding remarks. Okay, so here is a pictorial description of an isolated horizon. An isolated horizon is a 3D inner null boundary of space-time. These sections delta 1 and delta 2 are two isolated horizons, of course connected by a curvy section in between, which can be either time-like or space-like depending on whether matter is going in or coming out. So I will not talk about this dynamical horizon section. So my talk will be about this isolated horizon. So here no radiation and matter can cross the horizon. Okay, here are some properties just to ensure that this actually represents a black hole spacetime in more generic sense. So the cross sections of the isolated horizon, which I talked about, are of constant area, and since it's already I have told that this is an inner boundary of spacetime, so to make the action very differentiable, you have to have a Chern-Simons theory on the boundary. That already Professor Majhi talked about that. And it has an SU2 gauge impedance. So now the difference from the general event horizon case is that all the quantities are defined locally on this isolated horizon, whereas the event horizon is a very global description. So unlike the event horizon, in case of isolated horizon, matter and radiation can exist arbitrarily close to it, but it cannot cross the horizon. Also the surface gravity remains constant on the horizon. This is also derived from the very local boundary conditions which are imposed on isolated horizons. And also there is a notion of first law, like in case of event horizon, which gives rise to the definition of the notion of energy associated with the isolated horizon. So these are some basic properties which ensure that this represents an event horizon from a very local perspective. So this slide is just to show that why the event horizon is a special case of the isolated horizon. If we just impose the stationarity in the bulk, that is the local killing, the global killing vectors and etc., then the isolated horizon mass is exactly equal to the radium mass. It is the conserved charge which we calculate. Okay, now a few words on the quantum geometric description of spatial slices. So in LQG, the spatial slices are described in terms of spin networks. So there is a very small section of the spin network showing a simplified description. So these are the edges which meet at vertices, and each of the edges carry this SU2 spin representations. This J1, J2, J3, sorry, yeah, J1, J2, J3, and these are the vertices. So you add these kinds of patches and span the whole space. So that will be the quantum geometry. Now, let us come to what a quantum isolated horizon is. I mean the statistical mechanical structures, the quantum structures. So these edges of the spin networks impinges on this inner boundary, the cross sections of the inner boundary, and gives rise to the quantum area of the horizon. So each of the punctures which carry some spin j contribute a quantum area whose measure is given by this 8 pi gamma LP square root over of j into j plus 1. And just by adding these quantum areas, we get the quantum area of the total sphere. Now, if we talk in a different language in terms of configurations, suppose we consider a set of spins where there are a sub number of spin halves and S1 number of spin 1 and etc. So the total quantum area is then given by this formula. So this is the language which I am going to use in my talk. So this is again the intuitive picture of the quantum isolated horizon cross section which I just showed here, and this is a very magnified view of how the quantum area is generated by this network. Now, so this is what the isolated horizon Hilbert space looks like. And the crucial point is that here there is a sum over all possible number of punctures here, this set P which I have written here, and the states are the physical states which are considered here in this Hilbert space are such that the total quantum area is just order LP square within the order LP square of the classical area of the isolated horizon. So that's how this condition comes into picture. So I will explain that in more detail as we go on. And these spin values which I showed here, this this has an upper bound of k by 2, where k is given by the classical isolated horizon area by 4 pi gamma LP square. And of course this k is quantized, so this is an integer, 1, 2, 3 and so on. Okay, now the microstate problem. So given a puncture data, that is, suppose we know that there are some spins J1 through Jn or n punctures there, then the formula for the microstates is given by this expression. But now I have to calculate the entropy for the isolated horizon for a given area. At first for the indistinguishable punctures. So how do I do that? So now I will consider all possible spins. So suppose J1 through Jn all are varying from half to k by 2. Anything is possible. So what are the number of microstates then? Given n number of punctures, I sum over all possible spins here, and this can be actually expressed in the language of these spin configurations, which I will show in the next slides through multinomial expansion. Yes. So this is the expression where I have recast in a different form here, where you can see here already there is a term like x1 plus x2 plus dot 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 whole to the power n, from where it can be, by using this multinomial expansion, here I can express it in these terms, which is the expression which I am going to use afterwards, but with some approximation in the large scale. So this is one thing which I am going to point out here, that I have already summed over all possible j's here, and there is no restriction on these sums. This automatically follows from the fact that I have considered these punctures as distinguishable, because that's why the arbitrary sum over each of the j's I can do here without any restrictions. But in case of indistinguishable punctures, I do not really know how to do this sum. So that's why I am reviewing this case of distinguishable punctures at first, and from there through some analogy I will go to the case of the indistinguishable. So this is the expression in a compact notation, where this n factorial by pi j sj factorial already reflects the distinguishability, and this g sj is what I am going to approximate in the large scale limit. That is this expression. So if I do an approximation in the large scale limit, this g sj has a very simple form, which is 2j plus 1 to the power sj. So this is what I am going to talk about. But in the next order approximation, the leading term of the entropy does not get affected. What comes is the minus 3 by 2 log area correction, which was discussed earlier in the. So I am not going to talk about that log correction. So that's why I am going to consider only this expression and carry on. And the difference in the counting of this distinguishable and indistinguishable case will reflect in this approximation only. Okay. So here the entropy calculation begins. But before beginning, I will just make an assumption that the basic postulates of the equilibrium statement hold here, and there will be one most probable configuration which will give the number of microstates, which is overwhelmingly larger than the other subdominant configurations, and this is how the entropy expression looks like. So I have just neglected the subdominant configurations here. So what to do here is that I have to find the most probable configuration here, given the constant of the constant area, because I am only looking at those quantum states which will give the quantum area with a classical plus minus order LP square. So here is the definition of the area ensemble. So I am going to vary the expression of the log omega Sj, which I have just shown earlier, given this constant. So this is the area constant which is being imposed for the physical states which I am going to consider. So by calculating this, solving this equation, the most probable distribution comes out to be like this, where this n naught is nothing but the sum over all possible j's for this most probable distribution. And in this case, the Lagrange multiplier gets determined just by taking the sum over this Sj star. But I have not shown this value here, but it can be calculated. It's like 0 point something, 10 to the power minus 1 order. And by choosing this Barberousse parameter, which is kept free till now, which was kept free till now, we can get the Bekenstein-Hawking area law, and gamma is fixed to be a number, this lambda naught by 2. So this is what the calculation for the distinguishable punctures give us. Now from this calculation of the entropy in case of distinguishable punctures, we have got some clue to how to go to the indistinguishable puncture scenario. So here if you see, each of the individual puncture is contributing some measure Aj, that is the area measure, which is root over of j into j plus 1, etc. Again if this Sj denotes the number of punctures with level j, the total area is given by this formula, and the degeneracy is Gj, that is the 2j plus 1 which I showed earlier. Now this has trivially this is related to this case of distinguishable particle gas, ideal gas, which follows the MB statistics. So there also, if I consider the energy ensemble, where the total energy is given by this sum over Ni epsilon I, where I is the single particle energy level, epsilon I is the energy of a particle in the ith level, and Ni equals to punctures, distinguishable punctures. So this is the correspondence which I have obtained from the previous calculation. Just if we consider this kind of correspondence, that j maps to I, and this is it, Sj to Ni, Aj to epsilon I, and Gj to omega I, then this is the exact calculation of this ideal gas scenario. And of course the underlying quantum theory will give us the details of what this epsilon I or etc. will be. Like in LQG, Aj is given by this thing. So what can I do from here in case of indistinguishable punctures? It is simple that in case of indistinguishable punctures, I do not have any bound on how Ni can vary in case of bosonic gas, suppose. But in fermions we have Ni equals to 0 or 1 or like that. But in case of bosons, I do not have any restriction on Ni, and the microstate count is given by this thing. Similarly, in case of indistinguishable punctures, we have the same scenario if we consider that correspondence, and the formula should be given by this. So this is like it is following like something B statistics, but of course it does not mean that these punctures are some particles which are bosons. This is not the case. I am just saying that from this correspondence, if you count the number of microstates, of course this approximate one, because I have thrown away the approximations for large scale, this formula has to be given by this bosonic counting. That's all.
Is the total number of punctures,
Yeah.
does it have to be constrained to a fixed number?
No.
It can be anything.
Yeah. As far as that constant is maintained, that is the total quantum area should lie within a IH, that is the classical area, plus minus order LP square, and AIH is very greater than order MB square. That's it.
So in a sense, the corresponding chemical potential is zero because you can create as many punctures you wish.
Yes, but that is bounded because suppose if you saturate all the punctures by spin half, then you can get a upper bound on this what n can be. But then there will again be a arbitrariness through this Barber-Ramsey parameter. But in principle, it is bounded. It cannot be arbitrary in that sense. Because in this case, there is no meaning of a puncture with spin 0 because it will have no area. Okay. So this is the formula for our microstates, which I am going to use for the entropy calculation in case of indistinguishable punctures. So these are the same steps which I am going to follow. That I will extremize this expression for omega log omega Sj given this constant of constant area where this curly A is A by LP square. Yes. And the most probable distribution comes out to be like this. So this is the standard this bosonic distribution kind of thing. Okay, now while calculating the entropy, I had to apply this Starling approximation, where I considered this Sj very greater than 1 to approximate this thing. And finally, and of course, yes, this psi j is given in this thing, so this is a mathematical thing, and you don't have to worry about that. And I have only rewritten this k by 2 in terms of this thing. The reason for that will be clear as I proceed. Okay. Now this Sj star that satisfies two equations like the previous one. One I can just saturate, just put the Sj star in the expression for the area constant from which I get this, and I can define a total number of punctures n naught by summing over all possible j's for that most probable distribution. So these are the equations which I have to worry about, and of course this thing I have only written just which will be clear the physical significance of this, that this n naught, since it is the number of punctures, I have to consider this value of lambda and gamma in such a way that this n naught has to be large. Otherwise this whole thing does not hold any meaning if n0 becomes 1 or 2 or. Okay. So from there I have to so while calculating this entropy, if I go further, as I will demand that that has to be equal to the Bekenstein-Hawking entropy, I have to be careful about these facts, that the allowed values of lambda and gamma should be such that this n not very greater than order 1. And to satisfy this condition, what I will see is that I have to choose this lambda and gamma in such a way that at least for every value of lambda and gamma, this most probable distribution, the peak of the most probable distribution is very greater than 1. Because this is the case which I considered, because in any way when I plot this thing, it goes down like this, or for MB statistics. In case of bosonic, this will again something going down to be like this. So I will only look for this peak value which should be satisfying this condition. So that's how I will check that if this is satisfied or not. Is n not very greater than order 1. Okay. Now the other bounds on this gamma are this, which is of course this upper bound follows from this thing that J max should be greater than half, and the lower bound follows from the fact that since gamma appears as a multiplicative factor in the area spectrum, it has to be positive definite. So this is how the bound on gamma appears here, which I have to look for. And finally, for this in the large area limit which I am considering here, lambda should be positive definite such that Sj star, which represents the number of punctures for some values of j, should be positive definite for all j. And how do I find out these things? Okay, so the other thing, which the most crucial thing I missed out, is that I demand that this entropy is given by A by 4, that is the Bekenstein-Hawking entropy. So how do I obtain this value of lambda and gamma which respect those conditions and gives rise to this Bekenstein-Hawking entropy? I solve this equation and I'll just go back and this equation graphically and see if for large area limit I have some values of lambda and gamma which respect those conditions, and you will see that there are indeed. So here is the plot, and from here the plot which is meaningful for our calculation is this plot which has a broadening due to the impreciseness of the plot which I did by Mathematica. And this U-shaped curve is not meaningful in our case because you can see this small a, this axis is the area axis, this is the lambda axis here, and this is the gamma axis, and when I plotted I got these two curves, and only in this case for every a in the large area limit there is only single value gamma and d, but in this case you will have two values. So what will it indicate is that in the large area limit, in this curve I am getting two most probable distributions for each area, but that is unphysical because the spin distribution is physical, that cannot be, for a given area that can be give two different things here. So I will just exclude this U-shaped curve here and talk about this, and from here you can see. So I will just go to this next curve. So yeah, you can see that this curve is actually in the large area limit is getting independent of A. So the significance of this is that, and also you can check from there that all the conditions which I mentioned earlier, those are respected by these values of gamma in this large area limit. And this is getting asymptotic to some constant value. And
what's in the vertical axis?
So this is the lambda axis view. Along the lambda axis I am looking. This is the area direction, and this is the gamma direction along this one. So I just put it here so that I can show you the asymptotic nature of this curve. So it is getting independent of A. That is what I am trying to point out here. Okay, so this is what I try to point out here, and so from here I can conclude that if we consider these indistinguishable punctures or distinguishable punctures, the Bekenstein-Hawking area law can be obtained for a constant value of gamma. The physics is still remaining the same, but the only difference is that the order of gamma which is getting determined here, it is much smaller. So it is like in the order of 10 to the power minus 3 you are seeing here, this gamma. So this is the gamma axis, but in that case you get something in the order of 10 to the power minus 1. But otherwise, whether you consider these punctures to be distinguishable or not, the physics remains the same. That is, you can get the area law for a constant value of gamma in the large area limit. But the other thing I have already pointed out, so I am not repeating this thing, that this follows the BE statistics in a particular sense, which follows from the counting. It's not some bosonic particles or anything like that. But the other thing which I try to point out is that the calculation which I have done in case of indistinguishable punctures begins from the approximate microstate count. So it has not been derived from the original formula of the Kolmogender formula for a given set of punctures. But only if I can do from there, then I can see that what happens to the log correction, which is the most important thing which I am going to try further. So that can only be done if I find out some way how to impose the summation, sum over j's, so that I can start from that formula and arrive at this thing, and then calculate the next order correction after this BE state counting. Then I can see how is it affecting this log minus 3 by 2 log a and etc. And the other thing is that which I just realized when I was writing this talk. So generally these punctures are considered to be, so I'll just on the lights, I have already finished. So when this spin network ends up there, and these punctures are actually considered to be distinguishable in the full theory due to the fact that if we change this J1 and J2, this changes the quantum state, the quantum spin network in the bulk. So that's how that becomes two physically distinguishable states in the quantum theory, and we consider these punctures to be distinguishable. But I don't know whether this is wrong or right, but I wanted to say in front of this audience that if two links join to one vertices and there you can end up with some larger spin networks. Now if you join, change this J1 and J2, I am confused about this. How does it give rise to two distinguishable states in the bulk? So as far as I know, in the literature this point has not been explored yet. People consider these punctures to be distinguishable in the previous sense which I told. So this is what I am also looking at, the log correction and this. So that is. Thank you.
Okay. So, questions? Arthur.
Well, this is really not about your talk, but about your last comment here. The reason why people do things for a distinguishable, for an appropriate to distinguishable distribution. I think this argument that G1 and G2 correspond to two distinct states in the bulk, that was your remark, which is why you consider the punctures to be distinguishable, should not really matter, because there is another view of this entropy as an entanglement entropy, which I discussed in my talk briefly. So you can think of quantum states for the whole system, described by pure gate vectors, and then you trace over the bulk states. If you do trace over the bulk states and consider a reduced density matrix appropriate to the boundary states, which is appropriate to the punctures, then write down the von Neumann formula in terms of tracing over the reduced density matrix, then it shouldn't matter what the bulk states are. You've already traced over.
But the one thing I will just try to that we understand, but since in the full theory we have to, so I was thinking like that in the full theory at first we have to determine whether it is distinguishable or not, and then after tracing over we can count those states according to that. But so that's why that is the thing which I also realized while talking to other people, that before tracing out in the full theory you have to determine whether those are indistinguishable or distinguishable. So that's why I was worrying about these things.
No, but why should that matter? Okay, doing the trace is another matter, but as far as the definition is concerned, if you're going to trace over the bulk states, how you classify those states shouldn't matter. It's kind of averaging over all possible bulk states. So,
Yeah. I seem to be missing one point. You mentioned that one of the constraints is that the total, the punctures are such that total area is within area horizon plus minus LP square. So that constraint you are imposing. And then you are saying how many ways you can have it to calculate the entropy. But then you also impose that this entropy must be a horizon divided by 4. So you have already fixed what should be the entropy, what should be the total entropy. So
no, I did fix what should be the total entropy, because there is still so that I have the room to impose that thing. That I am demanding that it should be area by 4, because there is still the arbitrariness of the Barberio-Mirzi parameter. So that's why I am able to do that. Otherwise you are correct.
So
it would have just followed from the
So what you are
calculation.
trying to do is using this Hawking Bekenstein entropy rule,
Yes.
you're constraining, in your method you're getting the value of the gamma.
Yeah, by demanding that the entropy
Should be.
yes. It's same as what was done in distinguishable punctures also.
Anything else? Okay, let's thank the speaker and all the speakers for maintaining the time, and we'll go for lunch.